You were taught that gravity is a force so early in life that it probably feels beyond argument. Things fall, planets orbit, you jump, and the ground takes you back. End of story. Simple, clean, settled. But the unsettling part is that one of the most familiar experiences in your life is also one of the most misunderstood. Because the deeper physics goes, the stranger gravity becomes. And at a certain point, the honest version of the story stops sounding like common sense and starts sounding like reality itself has been quietly lying to you. Not maliciously, not dramatically, just patiently, as if the universe let us use a useful shortcut for a few hundred years, and only later admitted that the shortcut was never the thing itself. That is the first shift to let sink in. Gravity may be the oldest physical experience you have ever had, but it is not the same as understanding gravity. Feeling something every day does not mean you truly know what it is. You feel weight every second of your life. You see objects fall. You know what down means so intimately that it feels built into existence. But what if down is not what you think it is? What if falling is not what you think it is? What if standing still is the weird part, and falling is the natural part? What if the thing you have been calling a force is, at a deeper level, not a pull at all? That sounds like wordplay the first time you hear it. It sounds like one of those clever science phrases designed to sound profound without changing anything real. But it changes everything. Because once you really understand what that statement means, you stop seeing gravity as an invisible hand tugging on matter, and you start seeing the universe itself as geometry in motion. You stop imagining objects being dragged around by some mysterious attraction, and you start imagining everything, including yourself, moving through a reality that is not flat, not rigid, and not passive. A reality that bends. A reality that shapes motion before motion even begins. And if that sounds abstract, stay with it. Because this is exactly where most explanations lose people. They either become too simple and leave out the astonishing part, or they become too technical and bury the astonishing part under terminology. But the astonishing part is the whole reason this matters. Gravity is not just another topic in physics. It is the thing that determines how stars are born, how planets stay together, how time itself passes, how light bends, how black holes form, how galaxies hold their shape, and why the entire universe looks the way it does. Gravity is not just one actor on the cosmic stage. It is part of the stage, maybe more than part of it. Maybe it is one of the deepest clues we have about what the stage even is. And yet, for all its importance, gravity is still unfinished business. We know how it behaves with extraordinary precision in many situations. We can calculate orbits, predict lensing, map space-time around massive bodies, and detect ripples from black holes colliding more than 1 billion light years away. But when we ask the most uncomfortable version of the question, what gravity fundamentally is, at the deepest level, the answer becomes far less satisfying. At that depth, physics starts sounding almost humble. It says, here is the pattern, here is the geometry, here is the equation, here is what will happen. But when you ask why this should be the shape of reality in the first place, the silence gets louder. That silence is not failure, it is not weakness, it is where the frontier begins. And it is also where this story becomes worth listening to all the way through. Because gravity is one of those rare subjects where the more accurately you explain it, the more surreal it feels. The ordinary version is easy. Things fall because gravity pulls them down. The accurate version is so much stranger that once it settles into your mind, you start looking at simple things differently. A dropped mug, the moon hanging over a quiet street, a person floating in orbit, even the feeling of your own body in a chair. They stop being ordinary examples of gravity working and start becoming clues that reality is shaped in a way your instincts never would have guessed. To feel how deep this goes, it helps to begin with the version of gravity that dominated human thought for centuries. Not because it was foolish, it was brilliant. It still is. Isaac Newton gave humanity one of the greatest conceptual leaps in history. Before him, the heavens and the earth felt like separate realms. Apples fell here, planets moved there. One world was familiar and earthly, the other remote and divine. Newton looked at both and said, in effect, no. The same rules govern all of it. The same logic that makes a stone fall also guides the moon around Earth, and Earth around the sun. That was a staggering unification. It collapsed the distance between the human world and the cosmic one. His law of universal gravitation was elegant and powerful. Every mass attracts every other mass. The strength depends on how massive the objects are and how far apart they are. That idea unlocked the sky. Suddenly motion became calculable. Orbits were no longer mystical patterns. They were consequences. Tides, trajectories, falling objects, planetary positions, all of it could be written in mathematics. And not vague mathematics, predictive mathematics, precise enough to forecast eclipses, track comets, and eventually help discover planets nobody had even seen yet. That is one of the most beautiful things about science when it is working at its highest level. It lets you see something before nature shows it to you directly. Neptune was found like that. Astronomers noticed that Uranus was not moving exactly the way it should if only the known planets were influencing it. Instead of throwing out the theory, they trusted the mathematics enough to suspect another planet was tugging from the dark. They calculated where it should be, turned telescopes toward that patch of sky, and there it was. Imagine that feeling for a second. Not discovering something by stumbling into it, but by reading the invisible structure of reality so well that the unseen becomes inevitable. That is what Newton gave us. Not just a formula, a new relationship with the universe. And because his theory works so well, it is understandable that people came to think of gravity as settled. Why wouldn't they? When a theory predicts so much so accurately, it earns trust. The problem is that a theory can be spectacularly successful and still not be the deeper story. Newton described gravity with genius, but description is not always explanation in the strongest sense. He could tell you exactly how the force behaved. He could not tell you what it was in its essence. Why should masses attract at all? By what mechanism? Through what medium? Acting across empty space, instantly, without visible contact, even Newton himself was uneasy about that. That discomfort matters because it reminds us that a clean equation is not the same thing as metaphysical closure. It is possible to know the pattern without yet knowing what kind of reality produces the pattern. For centuries, that distinction could be ignored because Newton's model performed so well. If your equations keep working, most people stop asking what deeper thing the equations are sitting on top of. But nature does not care whether we have become comfortable. It only cares whether our model matches what it does. And eventually cracks appeared. Not giant cracks at first. That is not how scientific revolutions usually begin. They begin with annoyances, tiny deviations, friction between prediction and observation. Little details that most people would never notice but that refuse to go away. Mercury became one of those details. Its orbit did not behave exactly as Newton's laws said it should. Not wildly wrong, just wrong enough to matter. Astronomers measured the way Mercury's elliptical orbit slowly rotated over time, and the amount of that shift did not fully match the Newtonian prediction, even after accounting for the gravitational influence of the other planets. That kind of discrepancy is dangerous in science, because it can mean one of two things. Either something exists that you have not accounted for, or your theory itself is incomplete. Scientists, quite reasonably, first looked for the missing something. Maybe there was another unseen planet closer to the sun, perturbing Mercury's path. People even gave this hypothetical planet a name, Vulcan. It is almost poetic, really. When reality begins to resist your expectations, the human instinct is often to invent one more thing rather than surrender the frame. But Vulcan was never found. The discrepancy remained. A small wound in an otherwise majestic system. Then came Einstein. And what made Einstein's move so radical was not that he merely adjusted Newton's law. He did something far more disruptive. He changed the meaning of gravity itself. This is the point where many explanations reach for a rubber sheet and a bowling ball. You have probably seen it. A heavy object placed on a stretched fabric creates a dip. Smaller objects roll toward it, not because the big object pulls them directly, but because the fabric is curved. That analogy is useful up to a point, and dangerous beyond it. Useful because it helps you picture geometry guiding motion. Dangerous because it sneaks ordinary gravity back into the explanation. After all, why does the bowling ball sink into the sheet in the first place? Because Earth's gravity is pulling it down. So if you are not careful, the analogy starts explaining gravity by using gravity. That is not good enough. So let's try a cleaner way to feel the shift. Imagine that space is not a passive emptiness where things simply happen. Imagine that space and time are woven together into a single structure, and that this structure has shape. Not shape in the way a rock has shape, but shape in the way a landscape has contours. Now imagine that matter and energy do not move through this structure as though it were a blank background. They participate in it. They influence its shape, and then that shape tells matter and energy how to move. That is much closer. Gravity in Einstein's general relativity is not fundamentally a force reaching out to pull masses together. It is what motion looks like when space-time itself is curved. That sentence deserves to be slowed down because it is one of the most important and least intuitive ideas in modern science. Not what gravity causes, not what gravity resembles, what gravity is. Or at least, what gravity is best understood as in the most successful classical theory we have. Matter tells space-time how to curve. Curved space-time tells matter how to move. Simple to say. Immense to absorb. Once you see it, things you thought were separate start locking together with eerie elegance. A planet orbits a star not because the star is throwing out some invisible rope and reeling it in, but because the star changes the geometry around it, and the planet follows the straightest path available in that curved geometry. That phrase, the straightest path available, sounds contradictory until you realize that straightness depends on the space you are in. On a flat sheet of paper, straight is one thing. On a globe, straight becomes something else. If you fly long enough in what feels like a consistently forward direction on Earth, not turning left or right in any meaningful sense relative to the surface, your path curves around the planet. On a sphere, straight does not look straight on a flat map. It follows the shape of the world. Now push that idea beyond surfaces and into the structure of reality itself. In curved space-time, what counts as the natural path is no longer what your everyday Euclidean instincts expect. Objects in free motion follow what physicists call geodesics, the closest thing to straight lines available in a curved geometry. And if space-time around Earth is curved in a particular way, then an apple released from your hand follows a geodesic that leads toward the ground. This is where the emotional shock really starts if you let it. Because in that picture, falling is not an object being forced off its natural course. Falling is the natural course. Read that again internally. Falling is the natural course. What feels like the simplest example of a force acting on matter turns out, in this view, to be matter left alone. No push, no support, no interruption, just motion unfolding according to the geometry of space-time. The weird part is not the falling. The weird part is the standing. That sounds backwards, because your body interprets the world from the standpoint of resistance. When you stand on the ground, you feel solid and stable, so your mind marks that as normal. When you fall, you feel instability and danger, so your mind marks that as abnormal. But physics is not obligated to preserve the psychology of your nervous system. The floor beneath you is not passive. It is pushing on you. That push is what you feel as weight. This is one of the most brain rewiring insights in all of relativity. What you call your weight is not the feeling of gravity pulling you downward. It is the feeling of the ground preventing you from following your natural path through space-time. In other words, if the floor vanished, you would not suddenly be acted on by gravity in some new way. You would stop being interrupted. That is why astronauts in orbit feel weightless, even though Earth's gravitational influence is still strong where they are. This is one of the most common misconceptions in public imagination. People say astronauts are weightless because they are so far from Earth that gravity is almost gone. Not true. At the altitude of the International Space Station, about 250 miles above Earth's surface, Earth's gravity is still roughly 90% of what it is at the surface. The station and the astronauts inside it are not beyond gravity. They are immersed in it. Completely. So why do they float? Because they are falling. The station is moving sideways so fast, about 17,500 miles per hour, that as it falls toward Earth, Earth curves away beneath it. It keeps missing the ground, over and over. Not escaping gravity, not turning it off, but living inside a perpetual act of falling around the planet. And because the astronauts and the station are falling together, nothing inside is pressing them against the walls or floor in the ordinary way. No support force, no resistance, no felt weight. This is one of those points where people either grin because the universe just got more interesting, or go quiet because the floor beneath the reality shifted a little. If you are in that second category, stay there for a moment. That is the right reaction. The best scientific ideas are not always the ones that make the world feel tidier. Sometimes, they are the ones that remove a false tidiness and replace it with a deeper coherence. Einstein pushed this coherence even further with one of the most beautiful insights he ever had. If you are sealed inside a small enough box, you cannot locally tell the difference between being in free fall inside a gravitational field and drifting weightless far from any significant gravity at all. In both cases, you float. In both cases, objects released beside you simply hover relative to you. In both cases, ordinary weight disappears. This is the equivalence principle, and it is one of the conceptual doors into general relativity. It says, in essence, that gravity and acceleration are intimately related in a way far deeper than intuition suggests. Imagine you are inside a windowless elevator, far out in deep space, no planet nearby, no star close enough to matter. The elevator begins accelerating upward at 32 feet per second squared. Suddenly, your feet press into the floor. If you drop an object, it falls to the ground. If you shine a beam of light across the cabin moves while the light travels. So the beam appears slightly bent. Everything inside behaves as though a gravitational field has appeared, yet none has. It is pure acceleration. Now imagine the opposite. You are in an elevator near Earth, but the cable snaps and the cabin plunges. For a brief moment, you and everything inside fall together. A coin released from your hand no longer drops relative to you. It floats beside you. Weight vanishes. To an observer inside with no outside reference, this can mimic deep space drifting. This was one of Einstein's flashes of genius. Gravity is not just similar to acceleration in a loose analogy, they are linked structurally. And once you start treating that relationship seriously, space-time begins to emerge not as a stage, but as an active participant in what motion is. Now here is where the story becomes even stranger, because if space-time is what gravity really is shaping, then gravity should affect not just moving masses, but time itself. And it does. This is not speculative philosophy. It is measurable fact. Time passes differently depending on gravity. Not psychologically, not metaphorically, not as a trick of perception. Literally. A clock deeper in a gravitational field ticks more slowly than a clock higher up. That means if you take two extremely precise atomic clocks, synchronize them, leave one at sea level and carry the other to the top of a mountain, then bring them back together, they will disagree. The one deeper in the gravitational field, closer to Earth's core, will have experienced slightly less time. In fact, Back in 2010, physicists at the National Institute of Standards and Technology demonstrated this effect over a height difference of just 1 single foot. They placed 2 hyper-precise atomic clocks side by side, elevated one by 12 inches, and measured the difference. The higher clock ticked faster by about 90 trillionths of a second per day. Just 12 inches of height was enough for space-time curvature to alter the flow of time. This is such a bizarre statement that it almost always deserves to be heard twice before it begins to feel real. Gravity does not merely influence motion through space. Gravity changes the rate at which time passes. That means your head and your feet are technically aging at slightly different rates right now because your feet are closer to Earth's center. The difference is absurdly tiny, far too small to notice, but the principle is real. And when gravity becomes intense, the effect becomes dramatic. This is where relativity stops being one of those clever sets of equations and starts feeling like a direct challenge to human instinct. Because almost nobody grows up assuming time is negotiable. Space maybe, motion sure, but time feels absolute in a way that runs deeper than thought. You don't just believe time passes. You feel it as the background certainty of your existence. Relativity says that certainty is local, not universal. The stronger the gravitational field, the slower time passes relative to regions where gravity is weaker. If you lived on the surface of an extremely dense neutron star and someone miles away in deep space watched you through a telescope, they would see your processes unfold in slow motion. Your clock would tick slower. Your heart would beat slower. Your entire local world would move through time differently relative to theirs. And before this starts sounding too exotic to matter, remember that humanity already relies on this effect constantly. The GPS system in your smartphone would fail within hours if these relativistic corrections were not built into its algorithms. Satellites orbiting Earth 12,000 miles above us experience time differently from clocks on the ground. Part of that difference comes from their high speed, but a major part comes from the fact that they sit higher up in Earth's gravitational field, where gravity is weaker. Their clocks run about 45 microseconds faster per day due to gravity alone. If engineers ignored relativity, your GPS navigation would drift off by several miles every single day. So every time your phone guides you to a street corner with eerie confidence, it is quietly paying respect to the fact that time is not universal in the way common sense once assumed. That alone would make gravity astonishing, but it is still not the full extent of the damage gravity does to ordinary intuition. Because if space-time is curved by mass and energy, and light moves through space-time, then light should also follow that curvature, which means gravity bends light. This was one of the most dramatic early confirmations of Einstein's theory. Under Newton's picture, light did not fit neatly into the gravity story, at least not in the deeper geometric sense Einstein was building. But in general relativity, if space-time curves, then even something massless like light should have its path bent when passing near a massive object. Not because the light is being pulled in the old everyday sense, but because the geometry through which it travels is not flat. That prediction was tested during a famous solar eclipse in 1919, when stars near the sun's edge could be observed during total darkness. If Einstein was right, their apparent positions in the sky would shift slightly because their light had bent while traveling through the curved space-time surrounding the sun. That is exactly what astronomers found. The stars were not where flat space expectation said they should be. Their light had taken curved paths around the sun to reach Earth. That result did more than support a theory. It changed the emotional atmosphere of physics. Headlines across the globe declared that Newton's view of the universe had been overturned. Suddenly, general relativity was not just beautiful, it was real. Light itself, the thing many people unconsciously treat as the straightest thing in the universe, was being rerouted by gravity. Think about how wild that is. A star can change the path of light from another star without touching it. Not by throwing out a force beam in a cartoon sense, but by changing the architecture of space-time through which the light travels. Reality is not a passive hallway. It is a hallway whose walls, floor, and clock are all being reshaped by mass and energy. This becomes even more spectacular on cosmic scales. Entire galaxies and clusters of galaxies can bend light enough to magnify, duplicate, or distort the appearance of more distant objects behind them. This is called gravitational lensing, and it is one of the most visually poetic consequences of relativity. Massive objects become lenses, not made of glass, not polished by hands, but made of geometry. They warp the routes available to light, so background galaxies appear stretched into arcs, multiplied into rings, or mirrored in strange patterns across the sky. And here is the truly eerie part. Sometimes lensing lets astronomers detect mass they cannot see directly. Something invisible is curving space-time enough to alter light, so there must be mass there. That is one of the major clues that led to the modern dark matter problem. In other words, gravity is not just a thing we study for its own sake. It is one of the only ways the universe tells us about what is hiding in the dark. If you are still with me here, this is a good place to notice what kind of subject gravity really is. It begins with a dropped object and ends with reality itself becoming negotiable. A force becomes geometry. A stable floor becomes an interruption. Weightlessness becomes the natural state. Time bends, light bends. Invisible mass reveals itself by curving the paths of things we can see. Gravity is not getting smaller as the story goes on. It is swallowing categories you once thought were separate. And the more extreme the environment, the more ruthless that swallowing becomes. Because now we have to talk about black holes. That alone surprises many people. A black hole is not dangerous because it has some magical new kind of pull at great distances. It is dangerous because mass has been compressed into an extreme enough state that space-time near it becomes violently distorted. If you come too close, the available paths through reality start pointing somewhere you cannot return from. The boundary that defines this one-way region is called the event horizon. This is not a physical shell in the ordinary sense. It is a point of no return in space-time. Cross it and every future-directed path leads inward. Not because something grabs you with invisible hands, but because outward stops being a viable direction in the deep, geometric sense that matters. That is difficult to feel intuitively, because we think of directions as options: left, right, forward, back. But inside the event horizon of a black hole, going inward becomes less like choosing to walk into a room and more like moving toward tomorrow. It is simply where your future leads. You do not resist the future by stepping sideways. And inside a black hole, in the geometric structure described by general relativity, the singular center is not just sitting there like an object in space, it becomes woven into your causal future in a way that makes avoidance impossible. If that sounds surreal, good. It is surreal. From the outside, things get even weirder. An observer watching someone fall toward a black hole would not see that person simply plunge through the horizon and vanish in an ordinary cinematic sense. As the falling person approaches the event horizon, their time appears to slow more and more relative to the outside observer. Light escaping from them becomes increasingly redshifted, stretched to longer and longer wavelengths, dimmer and dimmer until they seem to freeze near the edge and fade away. But from the falling person's own perspective, assuming the black hole is large enough that tidal forces at the horizon are not immediately fatal, they do not experience some dramatic wall or frozen moment. They cross the horizon in finite time and continue inward. So one reality says the crossing seems to never complete. Another says it does. This is what gravity does when space-time itself is the medium of the story. Different observers do not just disagree about appearances in trivial ways. They can disagree in ways that reshape what happens even means. And then there is the singularity. The word itself carries a mythic quality now, but in physics it marks a place where our current description breaks down. General relativity, when pushed to its own internal conclusion, predicts a point where curvature becomes effectively infinite, and our equations cease to provide a meaningful physical account. That is not necessarily proof that literal infinity exists in nature in the naive way the word suggests. More likely, it is a sign that general relativity has reached the edge of its domain and must eventually give way to something deeper, presumably some future theory of quantum gravity that can describe what space-time and matter are doing when the scales become unimaginably extreme. This is one of the most important things to understand if you want a mature picture of science, rather than a cartoon version. Science is not strongest when it pretends to know everything. It is strongest when it knows exactly where its power ends. Black holes are a triumph of relativity and also a warning sign that relativity is not the final word. And black holes are not just geometrically extreme, they are physically brutal. If you fell toward a stellar mass black hole feet first, the gravitational difference between your feet and your head would grow rapidly. Your feet are slightly closer to the center than your head, so they experience a significantly stronger pull. On Earth, across a height of 6 feet, this gravitational difference is far too small to feel. But near a black hole, it becomes catastrophic. The result is tidal stretching. One part of your body accelerates downward vastly faster than another part. Eventually, that difference tears you apart at an atomic level. This has one of the strangest names in all of serious physics: spaghettification. It sounds almost comic until you remember what it actually means. You are stretched long and thin by differences in space-time curvature itself. And here, depending on the size of the black hole, reality offers different flavors of nightmare. Near a small black hole, those tidal forces can kill you well before you reach the event horizon. Near a supermassive black hole, like Sagittarius A star, at the center of our galaxy, which contains 4 million times the mass of the Sun, the event horizon is so vast that the tidal gradient at the boundary is gentler. You could, in principle, fall through the horizon of a supermassive black hole without immediately noticing anything locally dramatic. The horror is delayed. The geometry closes behind you before the violence truly begins. If that image does not stay with people, very little in science will. Because it takes one of the most cinematic concepts in the universe and strips it of the fantasy version. You are not torn apart because the black hole is sucking harder. You are torn apart because reality itself is becoming uneven around your body. There is another twist, and this one is so strange that even now it still feels like a leak from another level of understanding. Black holes are not completely black. In the 1970s, Stephen Hawking showed that when quantum effects are considered near the event horizon, black holes should emit radiation. This is one of those results that makes the universe feel less like machinery and more like a profound argument between theories. General relativity gives you the classical black hole. Quantum field theory says empty space is not truly empty, but alive with quantum fluctuations. Put those ideas together near an event horizon, and black holes slowly begin to radiate energy into space. The consequences are shocking. Over enormous stretches of time, black holes can evaporate. Pause there, because that sentence deserves its own moment. A black hole, the thing defined in public imagination as the ultimate trap, can slowly lose mass and fade away into nothingness. Not quickly. For a black hole with the mass of our Sun, evaporation would take roughly 10 to the power of 67 years, a timescale so vast that ordinary language barely survives it. But the principle matters far more than the number. It means black holes are not eternal monuments. They are thermodynamic objects. They have temperature, they have entropy, they live in the same universe as information, quantum uncertainty, and gradual decay. And that is where the real trouble begins. Because once black holes evaporate, we are forced to ask, what happens to the information about what fell in? This is not a picky academic puzzle. It cuts straight into the foundations of physics. In ordinary quantum mechanics, information is never supposed to be destroyed. Scrambled, yes. Hidden, yes. But never erased from existence. Yet if a black hole forms from matter, carrying rich information about its exact state, and then later evaporates into featureless thermal radiation, where did the information go? Was it destroyed? Encoded somehow in the escaping radiation? Preserved on the horizon in some subtle holographic way? Transformed into something our current language cannot yet track? This black hole information paradox is one of the places where physics feels least complete and most alive. It is not a solved mystery wrapped in good branding. It is a real wound in our understanding of reality. And still, gravity keeps expanding its reach. In 2015, a century after Einstein predicted them, humanity directly detected gravitational waves, ripples in space-time itself. Try to really feel what that means instead of letting the phrase pass by because you have heard it before. Not waves traveling through space-time. Waves of space-time. The geometry itself trembling. Reality ringing like a struck bell. These waves were generated by two massive black holes orbiting each other, spiraling inward and merging in a collision so violent that for a brief fraction of a second, the energy emitted in gravitational waves exceeded the total light output of all the stars in the observable universe combined. That sentence sounds exaggerated until you remember what kind of universe we live in. Nature is not interested in matching the scale of human imagination. It exceeds it casually. The detectors that measured these waves, the LIGO facilities in Washington State and Louisiana, along with Virgo in Europe, are miracles of engineering precision. They consist of massive laser interferometers with perpendicular arms stretching 2.5 miles long. They are designed to measure changes in arm length smaller than 1/10,000th the diameter of a proton. That alone feels impossible until you remember how much of modern physics is really a story of human beings refusing to let scale bully them. Too small, too large, too distant, too fast. These are not final barriers. They are invitations to build better sensors. And what those sensors heard was space-time itself, shivering from a cataclysm that occurred more than 1 billion light years away. This matters for more than poetic reasons. Gravitational waves give us a brand new way to observe the universe. Light can be blocked, scattered, absorbed, or delayed by cosmic dust clouds. Gravitational waves move through matter with extraordinary indifference. They carry pristine information from events that would otherwise remain permanently hidden from view. Black hole collisions, neutron star mergers, and possibly, one day, the faint quantum echoes from the Big Bang itself. It is as if humanity developed an entirely new sense and discovered that reality had always been speaking in another register. This is a good place to stop and notice why gravity continues to hold our attention so deeply. It is because gravity keeps changing category on you. First, it is a familiar force. Then it is geometry. Then it bends time. Then it bends light. Then it creates event horizons where futures close. Then it radiates. Then it shakes the universe in ways we can measure across billions of light years. Gravity refuses to stay simple, and something in us loves that. We say we want simple answers, but often what really holds us is when an answer turns out to be far deeper than the question we started with, and gravity is nowhere near done. Because once astronomers began studying galaxies carefully, another massive problem emerged. The stars in the outer regions of spiral galaxies were orbiting the galactic center far too fast. Based on the visible mass of stars and gas we could see, those outer stars should have had much weaker orbital speeds. The visible mass simply did not provide enough gravity to keep those fast-moving stars in orbit. By all laws of physics, those galaxies should have spun themselves apart, scattering their stars into deep space. But they did not. So either our understanding of gravity changes on galactic scales, or there is a vast amount of extra mass in the universe that we cannot see. The dominant scientific answer is dark matter. Dark matter does not glow, reflect light, or absorb electromagnetic radiation. That is why it is called dark. But it possesses mass, which means it exerts a powerful gravitational influence. It curves space-time, it holds galaxies together, it forms the invisible scaffolding around which the large-scale structure of the cosmos is built. We infer its presence almost entirely from what its gravity is doing to the light and motion around it. Think about how extraordinary that is. Roughly 85% of all matter in the universe is something we have never directly touched, captured, or seen. And one of the main reasons we know it exists is because gravity behaves as though that invisible mass is sitting right there. Gravity becomes a witness, a kind of physical testimony written in geometry. Then, as if dark matter were not enough, cosmology hit us with another insult to common sense. The expansion of the universe is accelerating. When astronomers measured distant supernovae in the late 1990s, they expected to find that the mutual gravitational pull of all the galaxies was gradually slowing down the expansion of space that began with the Big Bang. That made intuitive sense. Mass pulls on mass, so expansion should decelerate. Instead, they discovered that the expansion is speeding up. Something is driving spacetime apart faster and faster over time. We call this mysterious agent dark energy. Dark matter is invisible gravitating mass that pulls things together. Dark energy is whatever force or property of space is driving the accelerated expansion apart. Between them, ordinary matter, the atoms that make up stars, planets, mountains, trees, and human bodies, makes up only about 5% of the total content of the universe. If that does not humble a person, nothing will. We built human civilizations around the visible world and spent centuries assuming the obvious universe was the entire universe. Then we learned that even the matter we are made of is just a tiny 5% minority in the cosmic budget. And the phenomenon we thought we understood best, gravity, turns out to be the primary way the hidden 95% makes itself known. Because gravity is not just a chapter in a physics textbook, it is one of the main reasons the universe continually embarrasses our human intuition. And here is maybe the deepest embarrassment of all. Despite everything we have learned, gravity remains the odd one out in modern science. Physics possesses another astonishingly successful framework called quantum mechanics, which describes the microscopic realm of subatomic particles, forces, and probabilities. It underlies modern chemistry, electronics, lasers, computing, and nuclear energy. But general relativity and quantum mechanics do not fit together. Each works flawlessly within its own domain. Each has passed every experimental test ever thrown at it. Yet when we try to apply both to extreme situations, like the microscopic singularity at the center of a black hole or the very first instant of the Big Bang, their mathematical languages clash completely. Relativity assumes spacetime is smooth and continuous. Quantum mechanics asserts that everything at the smallest scale is grainy, probabilistic, and chaotic. This is not a minor bookkeeping error. It reveals that our two greatest descriptions of physical reality are fundamentally incomplete relative to each other. That is why physicists have spent decades searching for a unified theory of quantum gravity. Not because it sounds futuristic, but because nature demands it. Somewhere beneath relativity and quantum mechanics sits a deeper framework where space, time, and gravity reconcile. Maybe that framework involves hypothetical force particles called gravitons. Maybe spacetime itself is an emergent property. Not a fundamental fabric, but something built out of quantum entanglement at microscopic scales. Maybe at the Planck scale, at distances smaller than a trillionth of a proton's width, spacetime ceases to be smooth and becomes a churning, grainy foam. And that is the exact point where scientific honesty matters most. Science is not strongest when it pretends to have every answer wrapped up in a bow. It is strongest when it stands humbly at the edge of real unknowns. And gravity is the ultimate unknown. We know how to calculate its large-scale behavior with breathtaking mathematical precision, but we do not yet know how to reconcile it with the quantum world. We know what curved spacetime does to a planet or a beam of light. We do not fully know why reality chose geometry as its fundamental language, and maybe that is why gravity captures our imagination so deeply. It sits right at the intersection of everyday familiarity and cosmic mystery. Every human being has experienced gravity from the moment of their birth. Almost nobody has sat quietly with how bizarre it becomes when you step past the schoolbook definition. The coffee cup falling from the kitchen counter, the moon orbiting Earth in silent free fall, the astronaut floating weightlessly in orbit, the atomic clock on a satellite ticking faster than a clock on the ground, the beam of starlight curving as it passes the sun, the event horizon of a black hole closing off all futures, the spiral galaxy rotating inside a vast halo of invisible dark matter, the universe expanding faster and faster into an endless quiet dark. It is all gravity. Or more accurately, it is what reality looks like when mass, energy, space, and time interact. And this is where we ought to slow down, because there is a philosophical trap people often fall into when learning about relativity. They hear that gravity is geometry, that time slows down, that light curves, and that space-time ripples, and they start treating the physical world as if it were an illusion, as if science had dissolved reality into abstract mathematics. But the opposite is true. Reality is not becoming less real. It is simply proving to be far richer than our evolutionary instincts prepared us to see. The floor beneath your feet is real. Your weight is real. A planet's orbit is real. A black hole is real. A gravitational wave passing through Earth right now is real. The strangeness does not exist because these phenomena are imaginary math tricks. The strangeness exists because mathematics turned out to be the only tool precise enough to describe a universe that was never engineered to cater to human-scale common sense. We evolved to survive at medium speeds, medium sizes, and weak gravitational fields over short human lifespans. Of course, physical reality feels bizarre when we look at extreme densities, cosmic scales, or light-speed motions. The surprise is not that our instincts fail at those limits. The surprise is that a species living on a small rocky planet managed to figure out the math anyway. And that is where gravity becomes quietly, profoundly beautiful. Because for all its strangeness, gravity is the sole reason the universe has any structure at all. Without gravity, primordial hydrogen and helium gas would have expanded forever into a uniform, featureless void. Matter would never have gathered into dense clouds. Stars would never have ignited. Without stars, heavier elements like carbon, oxygen, nitrogen, and iron could never have been forged in nuclear furnaces. Without those elements, there would be no rocky planets, no liquid oceans, no organic chemistry, and no long evolutionary line leading to conscious beings who can sit in a quiet room and wonder what gravity really is. The very same phenomenon that crushes collapsing stars into black holes is the phenomenon that made your existence possible in the first place. That is not poetry, that is physical history. The iron atom carrying oxygen in your red blood cells was forged inside the core of a massive star that gravity held together for millions of years, until gravity eventually triggered its supernova collapse. The calcium in your bones, the phosphorus in your DNA, the carbon in your cells. These are the structural remnants of stellar architecture shaped by gravity. Stars are gravity's long-burning compromises with nuclear fusion. Supernovae are gravity's violent renegotiations. Planets are gravity's leftover sculptures. And life is what happens on one of those sculptures when chemistry is given enough time and stability to begin observing itself. So when people say that gravity holds you down, that is a useful shortcut for daily life. But it is a tragically small version of the truth. Gravity did not just hold you down to Earth. Gravity wrote the physical conditions under which anything like you could ever exist. And still, the most brain-rewiring realization of all remains the simplest one. You are not being pulled downward right now. You are being prevented from falling. That single insight catches in the mind because it transforms something completely personal. It is not just about distant black holes, dark matter, or expanding galaxies. It reaches straight into your physical body in this exact second. The chair beneath you, the floor under your feet, the feeling of weight in your chest, the sense of balance in your inner ear. They are not passive defaults. They are active, continuous interruptions of your natural geodesic path through curved space-time. If the floor beneath you suddenly disappeared, you would not be acted upon by a new force. You would simply be left alone, moving freely along the geometry of the universe. Standing still on Earth is the resistance. Falling is the state of freedom. And when you step outside tonight and look up at the sky, remember what you are actually standing on. You are standing on a giant sphere of matter that has bent the space and time around it. You are watching the moon fall forever in a circle around our world. You are bathed in starlight that took decades or centuries to travel through warped geometry just to reach your eyes. And beneath your feet, the solid Earth is pushing up against you, holding you steady in a universe that is bending, moving, and reshaping itself in every passing second.